this module, you will learn about the binomial theorem for positive integral indices. In the earlier classes, you learned many identities such as a plus b whole square and a plus b whole cube. Now, consider the identities shown here. From these identities, we see that if the index of the binomial is 0, then the number of terms in the expansion is 1. If the index is 1, then there are 2 terms in the expansion. You can see a similar pattern in the remaining identities. We draw some conclusions from our observations. Firstly, the number of terms in an expansion is 1 more than the power of the binomial. The powers of the first quantity, a, decrease by 1, whereas the powers of the second quantity, b, increase by 1 in each successive term. In every term, the sum of the powers of a and b is equal to the power of the binomial. Now, let us arrange the coefficients of these expansions. We know that the coefficient of the first and the last terms is always equal to 1. The coefficients of the second row are added to get the coefficient of the third row, and the coefficients of the third row are added to get the coefficients of the fourth row, and so on. This structure looks like a triangle. This was developed by a French mathematician, Blaise Pascal. It is known as Pascal's triangle. Using Pascal's triangle, we can write the coefficients of the expansions of binomials with higher powers also. The coefficients of expansion of the binomial with the power 5 are 1, 5, 10, 10, 5, and 1. However, when the power of a binomial is very big, then writing the coefficients in Pascal's triangle is a lengthy process. What do we need to do in such a case? Here we make use of the concept of combinations to write the coefficients. We know that NCR is equal to n factorial upon r factorial multiplied by n minus r factorial. NC0 and NCn is equal to 1. Now, let us create a Pascal's triangle using combinations. Using this pattern, let us write the expansion for x plus y whole raised to the power of 8. Using the pattern, we can write the coefficients as shown here. Now, let us write the expansion. Here is the expansion for x plus y whole raised to the power of 8. You observed that it was quite cumbersome to work out the expansion. When the power of the binomial increases further, it gets very difficult to expand a binomial with this method. Let us now learn a general method to find the expansion of a binomial with the index n. The method is known as the binomial theorem. Let us now learn the binomial theorem for positive integral index. The theorem states that x plus y whole raised to the power of n is equal to nc0, x raised to the power n, plus nc1, x raised to the power n minus 1 into y plus nc2, x raised to the power of n minus 2 into y raised to the power 2, and so on up to nc n minus 1. x into y raised to the power n minus 1 plus ncn y raised to the power n. Here, nc0, nc1, nc2, and so on are known as binomial coefficients. Let us prove the theorem using mathematical induction. Assume the given statement as P of n. When n is equal to 1, P of n will be x plus y raised to the power 1, which is equal to x plus y, which is a true statement. Let us suppose the statement P of k is true for positive integer k. Name it as equation 1. Now, we need to prove that P of k plus 1 is also true. Consider x plus y whole raised to the power k plus 1. X plus y whole raised to the power k plus 1 can be written as x plus y multiplied by x plus y whole raised to the power of k. Here, we substitute the value of x plus y whole raised to the power of k. Now, let us write the product of these two expressions. After grouping all the like terms, we get this expression. We know that kc0 and k plus 1 c0 equal to 1. kcr plus kcr minus 1 is equal to k plus 1 cr, and kck and k plus 1 c k plus 1 equal to 1. Using them, the expression can be rewritten as shown. We observe that P of k plus 1 is true whenever P of k is true. Hence, P of n is true for all positive integral values of n.